All right, we're in C# world. Hi, Matt. Introduce yourself for people who don't know you.
Hey, I'm Matt Torgerson. I'm the program manager for the C# language.
I'm Chris Burrows. I'm one of the developers in the C# compiler.
Excellent.
I'm Sam Ing. I am, like Chris, I'm one of the developers on the C# compiler.
And I'm Eric Lippert. I am also one of the developers on the C# compiler.
Good to see you again, Matt.
It's good to be back.
So, you guys are introducing some new interesting features in 4.0. Today we want to actually kind of dig into them. So, right off the bat, let's just talk about what are some of the new key features that developers are going to be excited about, or that you're excited about.
Well, so obviously the big one, I think, the one that people are going to notice most, is going to change how people write code the most, perhaps, is what we call the dynamic feature, which is introducing a dynamic keyword that'll allow you to do things dynamically.
Okay.
So the bigger context for that is a bigger and bigger part of the world, the .NET world as well, is becoming dynamic in the sense that we can't know statically what's going on. We have dynamic programming languages like Python and Ruby that are being implemented on .NET, and we have APIs that have a very dynamic nature, like the HTML DOM and stuff. And working with these dynamic things is really painful from a very statically typed language, because in a static typed language you assume that you know the shape of things when the compiler runs, and this is working with stuff where you don't know the shape, and you'd like to just pretend you know it and get going like you can in dynamic language. So for us, the dynamic feature is at the very high level about interfacing with this whole world and giving you a good experience doing that.
So by just saying dynamic foo, all of a sudden that I just created a dynamically typed something? Is that what you're saying?
Yeah, by saying dynamic is a type. So,
I get that. Okay.
So if you say dynamic foo, what you're saying is I have a variable called foo and its type is dynamic. So dynamic is a static type. And you can assign pretty much any old thing to a dynamic. Good old C# objects like 7. You can assign to it, or objects that are really weird and special and know how to dispatch themselves in fancy ways at runtime. You can also assign to this. And once it's assigned to dynamic, you don't really care what kind of thing it is. You just allow people, the compiler allows you to do whatever you want with foo, so you can call whatever method you want on foo with whatever argument you want, and the compiler's not going to complain. Instead, it's going to keep stuff around, like the name of the method here and the argument you passed. Keep them around, stuff them somewhere for runtime, and at runtime it will then be dispatched according to whatever the object is. Right? So 7 wouldn't have an M, so you'd get a runtime error here instead of a compile time error. But you may have objects that respond to this, or you may do something that 7 actually knows. What does 7 know?
Two-string.
Two-string, yeah, perfect. Yeah, you could actually have done that with just objects. So, but yeah, you'll essentially ask the object at runtime. So I'm trying to say two-string to you. What do you want to do?
Okay. So let's get a little geeky here, which is a good thing, and dig into, since you guys are compiler people, up in composition world we type in dynamic, but I think we have a high-level understanding of what happens, but what really goes on inside the compiler when you confront that dynamic pattern? What do you do down there?
So there's kind of two parts to what we do. The first part of it is, like Matt was talking about, from a static perspective, what does the compiler code gen for you? One of the things that we do is we interact with the DLR team a lot. And one of the things that they've been doing is they've been coming up with this paradigm which basically allows you to dynamically dispatch something, some kind of action on an object. And they have a bunch of standard actions. So like Mads was saying, there's like what we call a call action, which is just like a regular method call. We have things like, they call them a get member action, but this is what in C# looks like a property access. So if you did like console.writeLine of this thing. And they basically have a whole bunch of standard actions that allow you to encapsulate intent without knowing at compile time what that intent is. And so from the C# compiler's perspective, when we first compile this method, we basically wrap up all that we know statically about what the user's trying to do, and we wrap it up into a couple of DLR specific objects that basically encapsulate what it is that, like, the best that we can do from a static time perspective. Then the second half of it is at runtime, when you actually start running the code, what happens underneath, how we end up, calling into whether, like Maz was saying, depending on what the object is, different dispatching things may happen, right? So for instance, if this was like an object that you got from IronPython, for instance, it will know how to do its own dispatch, and this call to foo.toString will end up being dispatched by the IronPython's object instead, and so on and so forth.
Interesting. So you guys are, let me just get this straight though. I mean, is the DLR running? Right, you're saying the DLR team has done a lot of work, so I'm assuming that at runtime the DLR is there.
That's what the R is for.
Right. Yes, it is a dynamic language runtime.
Yeah.
So there are pieces in there that are designed to make it very efficient to do these kinds of calls. This is not just reflection. It's not like we're just spitting out for this particular example. It's not like we're saying, okay, well, go take the string myprop and go get me a property info off the type and then invoke that property. It is much, much smarter, and maybe like Chris and Sam can talk a bit about exactly how they work with the DLR to do that, because it's black magic as far as I'm concerned.
I'm sure. So let's do that. Let's talk about how you work with the DLR, and that's why I just wanted to get out there. I mean, you are working with the DLR here.
Yeah, yeah. So to go back to what the compiler emits, we are emitting calls to, well, for one thing, when you use the type dynamic, from the perspective of the language, dynamic is a real type, and you can say it pretty much anywhere that you can say any other type. You can have list of dynamic, and you can have array of dynamic, and you can have it in member signatures, and you can have it as the types of locals, and you can do a lot of things with it. And when we emit that, it's going to fall out in the assembly as object. And the language is, when you perform any operation on any expressions of that type, the language is going to do this funny thing where it tries to invoke the DLR. And the way it does it is, we have a runtime binder that is specific to C#, that C# talks to, I guess in a way similar to the VB language has their runtime binder that they use for late dispatch of COM methods and things like that. We have one. And we emit, more or less, we emit fields. We emit static fields that hold these things that we call call sites. And those call sites they represent the actual operation, per line of code. And so for each dynamic operation that you do, you get a call site. And we initialize that call site lazily the first time the code executes. And once we've done that, we simply dispatch to it. And when we dispatch to it, it goes to the runtime binder. And Sam knows a little bit more about the runtime binder than I do, but there's a protocol between the runtime binder and the DLR that enables them to cooperate on who should be doing the dispatch. So for instance, if you have 7 here, 7 is a normal .NET object.
Okay.
And that's something that the C# binder, there are specific C# semantics around the binding of methods on 7, and the C# binder knows how to deal with that. And so it says, if you happen to call toString on it, then that code in your method will turn into an initialization of a call site.
Okay.
With all the appropriate data, like the name toString and the object.
So what does that look like? Okay, thank you. He's writing it down. Sorry to interrupt you.
So what does what look like?
What really happens when that's being called? He's writing it for me. That's cool. Sorry to interrupt you. Channel 9 style. Cool.
You mean you don't do it when the camera's not around?
Exactly. Oh, yeah.
So what happens is when we talk about invoking the DLR, and when you asked about like, is the DLR running? Well,
yeah.
Really what that is this call site that Chris was talking about is really our gateway into the DLR. What the call site will do is we essentially create the call site by telling it hey, you know, I want something that looks like a call thing, and I'm gonna like it looks like a method call for me, and all I know about it is that we're not calling it, we're calling toString, is that its name is toString, and usually we have like some stuff that have to do with the arguments, so, but we don't in this case. So you know, we end up giving you a null array of these kinds of things. But essentially, we seed the site with information about, hey, what is it that I want you to do? Mm-hmm. And you can kind of think of this payload idea as the C#, what the C# compiler knows about the intent of what the user is trying to do. Right? So this thing looks kind of like a call to us, so we kind of tell the DLR, hey, this is a call-looking thing, so go off and do your magic on that. And so what we end up doing is we end up initializing the call site and then invoking the site. So there's like a lot more magic around here, like Chris was saying, you know, we only initialize it once, that kind of thing. But the site ends up having a target delegate, which I'll just call target for simplicity's sake. And we end up invoking this. We end up invoking this delegate with the arguments that we would have passed to the call. So let's pick a different call that actually has something. So let's say we called m with some arguments. So x 10. Right, we would initialize this guy, and this guy would be some set of argument information about the 3 arguments that we have, and then we would invoke the target with the arguments to the call that the user had made. Mm-hmm. Now, underneath the covers, what this will do is the DLR generates this delegate, this target delegate. The DLR basically provides a set of caching rules for us. And when we invoke this delegate, it will basically do cache checks on whether or not we can bind this thing. And so the simplest cache check that it will do is just type equivalence. Mm-hmm. So, for instance, when we call this thing, we give it 3 arguments, and it'll check the types of these, the runtime types of these arguments, and basically filter out based on based on the runtime types. And if it doesn't know how to bind the thing, then it will fall back to the object and ask it to bind itself. So.
And if it's not clear, I don't know how much people know about the DLR at this point and how much you've looked at it, but if it's not clear, the DLR is just a library. It's just a .NET assembly that sits there, and in fact right now it all lives in system core. And our call sites, you know, interact with it in a way, but it's just a library. It's nothing really special about, you know, it's not a new runtime component of the CLR or anything. So this is all just code that we've written on our team that.
But the actual DLR is not. It's not a runtime. I thought it was something that I thought it was a virtual machine that runs on top of the CLR. That's not what it isn't.
It's a regular assembly that runs on the CLR.
Perfect.
And I mean, it depends on what you mean by virtual machine, but it's pretty smart. It knows how to, you know, it knows how to take objects and it uses lightweight code gen to you know.
Yeah, we had a deep DLR on Channel 9 with John Lamb and the guy who wrote LOL caps or whatever. Or the language, he wrote a language over the weekend using the DLR to show how cool it was, and it got really popular. I can't remember what the language was called, no offense to those people.
Those guys surely know way more about the DLR than we do.
Right.
Yeah, or than I do anyway.
No, but I mean, it's really interesting. Okay.
But it's just to be clear, there's nothing new about the runtime. There's no magic. There's no more, you know, magic IL that we're emitting or anything. These are just method calls that we're emitting, and the DLR is just an assembly that's coping with them.
So very cool.
Right. You can think of the DLR as providing services which, if we were to make, you know, a real sort of baked-in virtual machine that was designed for dynamic languages, these are the sorts of services that machine would have to have. Right?
Okay.
And this particular DLR machinery is, you know, it's implemented in C#, and it's an assembly that runs on top of the regular old statically typed CLR. A couple of interesting things about what Sam has been pointing out here. First, the reason we're doing all of this caching is because you can imagine, what if this call is in a loop, right? It may be running hundreds and hundreds of times, and so we don't want to be in a position where every call is very expensive. It's not too bad if the first call is a bit expensive while we do a bunch of analysis. But the 99 times after that first call, we want that to be as fast as possible. We want it to burn a little memory and remember what happened before, because that's likely to happen again. Okay. The other thing that's interesting about what Sam said is Sam was being very cautious about saying, well, this looks like it's a method call, and people might say, well, isn't it a method call? Well, no, there could be a property called toString, and that property has a value, which is a delegate, right? In which case, that would not be a method call. That would be a fetch this field and then invoke this delegate. So we have to be very careful to make sure that all of the semantics of the C# language that are relevant get captured so that all of this stuff can be analyzed at runtime.
Interesting.
Right, so kind of to illustrate what Eric was just talking about, suppose we have an object array which has a whole bunch of different objects of different types, and then we for each over that array, and we want to call a dynamic method foo off of a dynamic object with this with whatever O holds. Well, for each iteration, the type of O is going to be different, and depending on what the type of O is, we're going to dispatch the call at runtime differently. So you can imagine, suppose I've got an overload of foo that takes an integer, an overload of foo that takes a string, and I don't have an overload of foo that takes a C, for example. Right, the first time we go through this thing, we'll want to bind this to the foo that takes an int. Well, what the DLR will do then is it'll basically, so the caching that Eric was talking about, what it'll do is it'll say, okay, well, let's look at my arguments. If my arg1's type is int, then do some kind of binding. And what this binding will do is it'll be the result of what the C# runtime binder will give us. Right? So initially, when we first encounter this call, the DLR just says, well, I don't know what to do with this thing, so all I know is that this is some kind of .NET object that the C# runtime binder can bind, and I'm going to ask you to go ahead and bind it. And then the C# binder will say, okay, well, I know all the methods on whatever type D is, so suppose D is my class C. And I know that I've got two different overloads of foo on C. Well, the first time you're calling me, the argument that you're giving me is an integer. And so the runtime binder will say, okay, well, for an integer, I know how to bind an integer on, a method foo that takes an int on my class C. So here's how you bind it. And basically what the C# runtime binder will return is it'll return an expression tree that is what the binding should be. So in this case, you can kind of think of it as, we have arg0 and arg1 goes to arg0.foo of arg1. And the expression tree that we give back here will have the correct method info for the foo that takes an integer. And so we'll return this tree to the DLR, and basically that'll get plugged in right here. And so the DLR's caching mechanism will say, well, okay, if when I'm calling this call site here, I've got an argument whose type is int, then I know how to bind this. This binds to c.foo that takes an int. And then the next time we come around, we'll say, okay, well, now O is going to be a string. And so when I call this type check is going to fail. And so when we fall out of here, what the DLR will do right here is it'll say, okay, well, none of my cache is hit, so I'm going to ask the C# binder to bind again. And this time I'm going to give it the string as the argument, and it's going to try to bind that as well. And then when we get around to having another integer, this type check will succeed, and so we won't need to rebind this method call for any more subsequent calls with the correct types that we've given it.
Cool. And if it looks like, that's just an example where we're using a regular .NET object, right? We're not using a COM object, we're not using a Python object. So if that looks uninteresting to you, and you might think to yourself, oh, I could do that myself. I could use reflection and just grab the foo method that takes an integer or the foo method that takes a string. Well, you could, but you're not getting the full semantics of the C# language by doing that, and we're giving you the full semantics of the C# language. So, for instance, the first parameter was a literal 1, and we know that it's a literal 1, and so we know, or a literal 0 is more interesting because of the conversion to enums, but we know what overloads that conversion is good for, and we'll find it in the same way that the static compiler would have found it to begin with. Or if your class C happens to have you know, a user-defined implicit conversion to string, you know, we'll do the right thing and make sure all the conversions are called, and you're getting the full semantics of the C# language, and not just what you would have done if you had manually tried to use reflection.
Interesting.
And also, in addition to that, all the rest of the stuff that DLR gives you, like dispatching to COM and Python and Ruby and everything.
So in fact, the C# runtime binder is kind of like it's a component of the C# compiler, essentially, that's been yanked out of the compile time and dumped into the runtime. And that's literally what we have done. That's how we make sure that it has the same semantics at runtime for binding that the compiler will have on non-dynamic calls.
Excellent.
Yeah, so kind of to follow up on what Chris was saying, that like we do get the exact semantics, and we also get the same error messages. So if we looked at the third one, suppose we didn't have an overload of foo that took a C, we will give you the exact same error message that the static compiler would have given, except at runtime, and this will appear as if in the form of a runtime exception that basically wraps the error message that you would have gotten at compile time.
So just to conclude, I want to quickly, what does the IL look like from this? You mentioned it's just an object. That's what it's mapped to an IL. So the jitter sort of doesn't get in the way of any of this at all. I mean, I just wonder how this affects what happens at runtime with the jitter. I guess nothing.
Well, for metadata, like I said, those dynamic things are being emitted as objects.
Okay, so as far as the JIT's concerned, it's just an object. So I'm thinking about it trying to, you know, do what it does, which is optimize code at runtime.
Well,
I'm just curious.
And the methods that we're emitting are, you know, the methods that you have a user, you've written them, and you have dynamic operations in them. And the IL that's emitted there, like I said, is just normal IL. It looks exactly as though if you happen to know what the methods were that we called, and you happen to know what the thing that we were going to generate was, you could type in, you know, what Sam had on the board before. We're just create a new site and then call .target on it. It's just regular old IL.
Okay.
So there's, you know, the jitter is not at the level of your method. The jitter is not getting involved with the with what happens in the runtime after we call that target thing. And Sam was talking about there's this cache policy in there, and it's looking at types and evaluating things, and that cache policy is sitting in a lightweight code gen method, which is the value of the target delegate, and it's being updated by the DLR itself, but it's just, you know, it's IL that we're generating, or that the DLR is generating at runtime with help from the C# runtime binders analysis.
Excellent. So you hand it off to the DLR and then rock and roll, and those guys do their black magic.
Right.
Your black magic.
Those guys are the experts.
They've done some very interesting black magic.
Yeah. So as a result, if you have one of these call sites that gets executed over and over and over again, but the types remain the same every time, so that you don't need to bind or do more analysis, then you're just invoking a delegate over and over again, and it's no more expensive than that.
So now let's talk a little bit about, let's bring it up to like the level of composition and developers who are going to be typing this word into their IDEs. When do you think people would be using this? So it's one thing to understand, I want to interoperate with Ruby or Python or some dynamic language, so therefore I'm going to just call this variable that's going to be, I'm going to get from this language and make it dynamic. Let's talk about when would I just start playing, when would I use this code in my day-to-day C# life? Okay?
Right, so there are a couple of different scenarios for when you would use it. One is where you have objects that are genuinely dynamic, and they may come from other languages, and it's an interrupt kind of thing. But there may also be APIs that genuinely return you stuff that is dynamic, and you want to get something back of type dynamic when you call a method, and you want to party on it. Indeed, if you want to exploit that, you can write your own. You can write your own dynamic code, and you can use it. 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 And objects that are dynamic. Like you could write your own expander object that just has a dictionary inside, and whenever you ask for a property on it, it'll say, "Oh, I don't have that yet. Let me just make it." And you can now literally write objects that fake out all sorts of behavior in whatever object model you like, and just access it as normal properties or methods or whatever from C#. I think a lot of the scenarios where you also see that's scenarios where things just become easier. Very important scenario there is interrupting with COM, like the Office automation APIs, where a lot of times what you get back from a call to Excel or whatever just comes back weakly typed as object, and we're actually we're making a little feature specifically for these COM APIs where you can get things back as dynamic instead. Because typically what you want to do is just, typically what you end up doing with such an API is today that you have to cast it to a strong type that you happen to know, and then you can start doing things with it. And there's a lot of cast and a lot of COM interrupt code. And here you can just, because it comes back as dynamic, you can just say dot and do whatever you would have done. You lose the static typing, but you get much more readable code. I think there are a lot of scenarios where you just want to make things flow nicer and have more compact and more readable code and get the casts out of there because they're really just in your way, and not really adding anything to your type safety, because you have to know what to cast to anyway, and you might as well just call what you know you have to call.
Sure. So this sort of replaces like what you used to have to do by just returning object, right? Because you have to cast it, but that is sort of somewhat dynamic. Not really, just returning object and let you figure out what the hell it is at runtime.
Yeah.
This is a strongly typed dynamic construct that you guys have created, which is really interesting. But it's not the only thing that you've done in C# 4.0 world.
That's
So come on, partners. What else have you done? I mean, clearly you must have spent a lot of time. I think we're being a little too simplistic with how much work you guys actually had to do to pull this dynamic keyword off.
It was a lot of work, none of which I did.
It's really a lot of work.
So what the hell have you been doing, Eric?
I worked a bit on a new feature we're calling covariance and contravariance, and I worked on the design team for all of this stuff. But I've been actually spending most of my time this release thinking about sort of what's coming next. Sort of the very far off in the future stuff that I can't possibly talk about because we don't know what it is.
Certainly. Excellent. All right. Well, let's continue on. Let's talk about what you have some other features that you're really stoked about.
So one of I think the next most visible one that people will see is named and optional parameters. It's a feature that actually, if you've been programming VB, you already know and love it. It's really one of those features that we're just getting feature parity with VB here. There is a notion on .NET, and it's representable in metadata, of allowing you to declare parameters in a method or index or whatever, declare them optional.
Yes.
And say, hey, when you call me, you don't have to pass this. If you don't pass it, this is the value I'll use. So we're essentially giving you syntax to make those declarations in C#. And we're also giving you, on the consumption side, where you call things, we're giving you syntax to pass parameters by name. So give an argument, instead of giving it in the right position of a call, you give it with the parameter name. So you can, instead of saying,
yes.
Let's have an example. So if we back up and look at how you can declare optional parameters, let's just be really abstract and have P's and M's and whatever.
Yes, keep it simple.
So if you have a method that takes an X and a Y, very good generic names here, int X, int Y, you can say that Y is optional simply by giving it a default value here. Let's say that's 7. We like 7 a lot today. Which means whenever you call me, you don't have to pass me this, and I'll just use 7. Right? So when you call it, you can say M5, and given that there are not other overloads that get in the way, you would actually call this method, and it would really be called, and the compiler would rewrite it to just calling it with 5 comma 7.
So now how does the caller of M know that Y is optional by just looking at the signature?
Just look at the signature.
Okay, so in other words, let's say you wrote, got it, it's going to look like that.
Yeah, it's going to look like that.
Okay,
That's,
thanks.
That's how it shows up in the IDE. You can see not only that it is optional, but what the value is.
Why didn't you create an optional keyword?
Because this is simple.
You don't want to be like VB, right?
We want to be different, man.
Yeah.
We look
VB
at what
just says
you
it
know
how
what?
it is, man.
we try as best we can to differentiate those two languages, and since we've decided to have the same features in them, we do the best with syntax. You know, whenever they do something one way, we do it the other way, and the other way around. I'm sure you've noticed that.
I have noticed that. Excellent.
So,
okay.
So that's the optional parameter thing, and this, the fact that it's optional and the default value is persisted in metadata in a format that is standardized across the net. So VB, who already has this feature, they will understand this as well, and you can omit the parameter in VB as well. So.
Okay.
I should say about optional parameters, there's a place where there's traditionally a heck of a lot of them, and that again is in the COM, the typical Office automation libraries that you interact with. You can have up to 30 parameters, most of which are optional. Or maybe, I think 32 I heard as there are myths about how many there are, like the number of words for snow in Greenland. But anyway, so there it's just a pain to have to pass all these parameters, and for all of them you have to give the same missing.
Yeah.
And having optional parameters is really nice there. But there's also, this is not just for COM intro. There are lots of places where it's nice to have optional parameters. Think about, you want to be nice to people, and you make like 8 different constructors, taking all different permutations of 3 parameters, whether you give it or not, because you want people to just give the right initialization data. And you can do that easily with optional parameters instead. It's just easier that way.
Absolutely.
But the other thing is you can pass parameters by name. So I could say M of x:5 here, and that would mean use 5 as a parameter, as the argument matching the parameter x, and I could, if I wanted to be a little more, to use it for something, I can swap the order as well. I can say y = 3 and x = 5 here, and that works too, right? So you can give them in whatever order you want, and combine that with being able to omit them. You can, in a very terse way, just give the first, the second, and the 27th argument and leave the rest out. And the 27th you would give it by name, because then you wouldn't have to, and you actually can't in C#, put like 25 commas in between. Right? So you just give it by name.
Excellent.
It's just making things much more sense. People who've done VB, they'll say, oh yeah, old hat, but
Cool.
the C# programmers, it's really, really nice.
Absolutely.
Right. Now, there are some interesting gotchas with this feature, and that was sort of the reason why this was never done before. Like, people have been asking us for this feature in C# for years and years and years, and we've never done it because it massively complicates the overload resolution algorithm, and it never seemed to be really worth the trouble. The feature was good. It was clearly a good feature, but it doesn't have to be good. It has to be good enough to be, worth the pain that it causes us. And it caused Sam rather a lot of pain. Give us some examples of how this can go terribly, terribly wrong.
So, like Eric was mentioning, overload resolution becomes much more complicated. I mean, we already have a very complicated overload resolution algorithm for C#, and it becomes a lot more complicated when you start dealing with multiple overloads of the same method that have different optional parameters for different different arguments that you've got, and essentially as you and when you throw in names as well, you run into a lot of different headaches. So, for instance, suppose I'm a not very good library writer, and I decide to write a method called M that's got int x is 5 and int y is 10. And now suppose I want to do another overload. Let's say I want strings this time, but I decide to reorder the names of these things. Right? So now my first overload, I've got x in the first position and y in the second position. My second overload, I've got them reversed. And so when I have a call to m with x with some kind of value here and y with some kind of value, when we do overload resolution, well, the first thing we got to do is we got to figure out, well, okay, do the names of these things actually match the signature, right? So you can imagine a user can specify, something like this, and we'll just be like, well, okay, this overload of m doesn't have anything named z, and so the very first order of business in overload resolution is to just check, okay, well, all the names that the user specified, are they there? Once you've figured out whether or not they're there, then you got to go and rearrange them in for each method that you're considering, you need to rearrange the arguments into the order that it expects them based on their name. And then once you've done that, then you can start figuring out which method the user's actually calling. So suppose I called this with x and y and I gave this 2 integers. Then when I first consider this method, I'll say, okay, well, the first parameter is going to be 0 for int x, because x is in the first position, and y is the second parameter, and it's going to be 0, and this one actually does match. When we go and consider this one, first we got to swap these guys around so that this guy is considered as a first argument, and this guy is considered as a second argument, and then we got to do the convertibility checks on that as well. And then to kind of further complicate matters, if you decide to throw in optional values, you got to stick those guys in as well, right? So if I have this call, if I call m with x is 0 and z is 10, we got to do all the stuff that we talked about earlier on matching the names and stuff, and then we got to say, okay, well, this m has 3 arguments. X and z are parameter names on this m, so it's still okay. But I don't have anything specified in the second position. Well, now we got to go and see, okay, well, the second position actually gives me an optional thing, so I'm going to use the optional argument here and basically rewrite this call to look like m.
All right, so what do you have up there?
So we can get even worse than Sam's example here. So suppose you got a base class and it's got a virtual method m that takes 2 ints x and y, and then Sam's terrible library writer comes along and says, oh, well, I'm going to extend this and I'm going to swap y and x. Now, this is perfectly legal because the names are not part of the signature, right? So now somebody comes along and says, oh, well, I'm going to make a new derived, and I'm going to call, and I'm going to say x is 1 and y is 2. Well, which one does it pick? Does it pass this as the first argument and this is the second argument, or this as the second argument and this is the first argument? And when you've answered that, suppose you then downcast this thing to a b, to a base, and then you do the same thing. Well, now what happens, right? Because you would think that the compiler has no idea that this thing, which is of type B, has anything at all to do with this method here, right? So Sam, what do we do in this case?
So essentially what we do is we take the compile time type of the object that you're calling off of, and we find the most derived method that is contained in that type. So in this first example, the compiler thinks that D is of type D, and so we're able to find this guy. And so we say, okay, well, the names x and y are going to come from this overload here. In the second example, the compiler only knows that it's a base class, and so we can find this m, but not this one. And like Eric said, there's no way that the compiler will know that at runtime, this local variable b is actually of type D. And so the compiler says, okay, well, all I know is that it's of type B, and so I know that b has an overload for m, and it takes the names from this overload of m and is able to resolve them as we expect. And so you can imagine, if I had some more derived classes that derive from D, we're going to pick the most derived one. So suppose Eric's got another class E that extends from D, and this guy's not a D, he's an E. Well, the compiler will say, hey, I know that this is of type E, but E doesn't have an M, so I'm going to walk up my base class chain until I find one of my base classes that has an M, and I'm going to use that guy's names for the method that I'm looking at.
Excellent.
And another gotcha is, in Sam's original example, would be y being optional. That 10 is embedded in the call site.
Yes.
Right. So you're taking the optional parameters from the method definition and now embedding them in the call site.
Right.
So these names and optional values are really, there are probably some best practices to make,
Right.
make sure
Yes.
you don't make life difficult for your users.
Totally.
And so one other thing that we should note, so far we've been using easy examples where we're just, using constant values, but suppose these are method calls that have side effects, right? Suppose I call, I want to give x the return value of foo and the return value of bar, and suppose this is ordered. Well, right. So what you would expect is you'd expect lexically that, okay, well, if we ignored the name things for a second, what you would expect in C# 3.0 is that foo would get called, its value would get stored on the stack, bar would get called, its value would get stored as the second parameter on the, as a second argument on the stack, and then m would get called with the return value of foo as a first argument and return value of bar as a second argument. Well, now we're allowing you to basically swap this so that the value of bar is the first value. Is the first argument that you pass to m, and the value of foo is a second argument. That's okay when you're thinking just about m, but the lexical ordering of the method calls actually has to stay intact. And so what we end up doing is we end up generating temps for these things. You can think of it as temp1 equals foo, temp2 equals bar, and then m gets called with temp2 because that was x, temp1 because that was foo, and the 100 because that was the value of the z that we have as the default parameter value.
Excellent.
So as the user, you're getting what you expect. But if you write reflector, maybe you you need to consider that.
Yeah.
Interesting.
I think an overall conclusion here is that we're taking away a lot of pain from the developers, and then we're applying it to ourselves.
It seems to be the case, or to these guys specifically, compiler people.
I'm applying it to them instead of
Yeah, you are, man. You're the slave driver. No, just kidding. So, but that does bring up an interesting question that we could focus on you, is why did you make the decision to make the lives of these compiler dudes so hard?
Well,
Customer
you mean by
feedback.
hiring them?
By letting it be like a...
Well, ideally, the pain we suffer shouldn't matter, right? We got great stuff out of there because of their sweat and pain.
Sure.
And that should be easy enough to answer. Yeah, we'll subject these guys to pain anytime rather than the customers.
So, what would happen if you're, probably nothing given the conversation we had at the beginning about dynamic, but what if you did dynamic typing that you then said in your overload and you did your craziness? I mean, that could further make you upset?
Well, so we actually have that support for that as well. So one of the things that we've had to do when we're thinking about this dynamic thing is, well, all of the new features that we're doing in C# 4, you've got to be able to use them in dynamic as well. So you can imagine if we had dynamic d equals something, and I did d.m, and I passed you some named arguments and stuff, you would expect that to work as a user. And so, like Matt says, we go through, I guess, great pains, I don't know, some kind of pains, to make sure that this kind of thing does work.
And every feature we do basically interacts with every other feature, and so we have a vast amount of pain for every little thing that we have.
Yeah.
It's cool. That's fun problems for you guys to solve, though.
Yeah.
Right on.
Yeah, there was a guy who used to work over in the Office team who's not at Microsoft anymore, but he writes a blog about these kinds of things, and he calls it N-squared development, right? Where every new feature you add means that you have to figure out all of the interactions with every previous feature, right? So if you have 10 features, adding the 11th, you got to figure out at least 10 interactions, right? When you add the 12th, you got to figure out 11 more interactions. So now you figured out 21 interactions. When you add the 13th, and it just gets bigger and bigger and bigger, and it takes us longer and longer to figure out how everything's supposed to work. Yeah.
Excellent. So we covered all the basic features. I mean, we didn't really touch on the COM.
Well, there are a couple more features I think we should just summarize those briefly.
Yeah, sure.
So one that's closely related to this, we've already mentioned COM a couple of times in connection to both the features we dived into. That's because COM is very important to us. In the sense that when .NET came out, it was sort of like we figured, it was its own world, it was going to take over the rest of the world, and COM was going to go away, and everything was going to be different. And of course, that's not the way the world really works, because there's a lot of assets that depend on COM, and a lot of great stuff out there that can't just expect people to rewrite from scratch. And so this time we're taking seriously, in a way that VB has done for a while, to have a nice story for programming Office. And these features play into that. Both dynamic and the named and optional make it really a lot nicer. And there are a couple of more tweaks that we do to just make that experience nicer. Like for instance, a lot of arguments, a lot of parameters in some of these automation libraries pass by ref, just because that was the way you did things back then. And passing by ref is slightly painful in C#, and it's extra painful if you actually don't want the result back. You have the 7 you want to pass, but you can't pass it by ref because it's not a variable and so on. And we just took that part and said, hey, we allow you to just omit all this ref stuff, just pass your values and we'll create temps for you and pass them along to COM calls. A couple more things like that I won't go into, just so that it feels natural. And then the final feature is one that I think Eric is warming up to quickly show something about over here. It's a feature that's been in the CLR ever since we added generics. It's called covariance and contravariance. And Eric is ready to tell a little story about it.
Right. I will just give the very briefest possible overview of this thing. If you guys are really fascinated by how it all works, I've written a 11-part series on my blog. Go read that. But very briefly, suppose you have a class, animal, a base class. You have a derived class, giraffe. Right? Every giraffe is an animal. Right? You can take any value of type giraffe and assign it to a variable of type animal. So you'd think that, well, I can take a sequence of giraffes, right, in some value, and then I could take a variable of type sequence of animals and say, well, this sequence of giraffes is a sequence of animals, and why shouldn't that work, right? Because you think, well, if what I'm expecting is animal, 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 and I get giraffe, 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 that should work just fine, right? This assignment is not legal in C#3 because we did not support covariant coercions of this sort. And by covariant is this highfalutin word from type theory. Basically, it says that if a giraffe fits into an animal, then an I-enumerable of giraffe fits into an I-enumerable of animal. It means that the direction of this arrow remains the same, right? It is covariant. If the direction of the arrow were reversed, then it would be contravariant. An example of contravariance would be take I-comparable, right? You have an I-comparable, you have an object that can compare two things, and maybe it's something that can compare any two giraffes, right? Well, if you have something that can compare any two animals, then it can also compare any two giraffes, right? So you could take something that's of type I-comparable of animal and assign it into a variable of type I-comparable of giraffe, even though you can't take a value of type animal and assign it to a variable of type giraffe. So that the flow has been reversed, right? The direction of the neutron flux has been reversed there. We have added this feature for interfaces and delegates, which are generic and parameterized with reference types, such that the interfaces and delegates are known by the compiler to be always safe when you do this. And the details of how we work out, given a particular interface declaration, is this always safe to be covariant or contravariant, are complicated, and see my blog for details.
Okay. Excellent.
Yeah.
Well, hey, thank you guys for your time. It's been awesome learning about this. This is exciting stuff. More dynamic in C#, which is very cool. And nice to meet the guys who actually write the language in the sense of the compiler, where the meaningful stuff happens. Thank you so much for your time, you guys.
Thanks.
Cheers.
Hey, you're welcome.